to the fourth of our 5 sessions today. We are moving a bit to the west in terms of the speaker landscape to Franck, who's sitting in the western part of this beautiful country. He is with DBI Services, and I have stopped counting the number of blog entries he's been providing and answers. I think it's well beyond 500. And the funny thing is, there's probably no one who has seen so many different databases and approaches being compared to each other. And that raised the quest for, hey guys, why are we doing all this, not only SQL? What is SQL good for, and why is it so attractive for developers? For me personally, Thomas, SQL was the third language which I learned to write. The first 2 ones were Fortran and Pascal. And the interesting thing is, SQL remained. Pascal is still in my brains, and I've forgotten Fortran. And the stupid thing is, it seems like SQL has something to it which sticks to our minds and makes us productive. And I think this is exactly what Franck will today explain to us. Remember, SQL was just started with one white paper by a person in a math department. It was about relational algebra. SQL is just an implementation thereof. There could be many. And the implementation and their variations over time seem to be very good. With that, I'd like to hand over to Franck, who's about not just to give us some insights on why and how, but show it. And be assured that he'll have simple surprises for you that make you say, hey, thanks God we have SQL.
Yeah, thanks, Thomas. So this is a presentation that is only a demo. I have no slides, and I will demo the basic things of SQL, but I will start with NoSQL. My idea is that even if NoSQL appeared after SQL, if you think about it, before SQL was invented, people were doing NoSQL. And I will start with that and introduce the concept, not only SQL, but relational databases. So I'm Franck Pachot. I'm working on databases for more than 20 years, mostly Oracle, but other databases as well. I'm working at DBI Services, where we do consulting, where we do training, where we do license audits, and also we have our service desk doing remote administration for our SLA customers. And we do all that remotely as well, as this year this is quite common. So I said that I will start with NoSQL, but I will do everything in the same database because Oracle database provides a NoSQL API, which is called SOUG. I am connected to an autonomous database on the cloud, which is free. You can set up the same. And I will provide you at the end a link to a Jupyter notebook where you can replay everything that I've done on my database, or you can create also your free database to do the same. So just wondering, sorry, I will just move a bit the things. Okay, I will start with Python. Let me just resize the screen because I'm not sure you see the last line. Not better. Okay, I want you to see the green line, so I'm sure that you see everything. So I will start from Python. Why? Because in NoSQL, or because before SQL, everything was done from a procedural language like Python. And I will use the driver to connect to Oracle database, CX Oracle. And I'm connecting there. And I will use SODA. SODA is a simple object document API, something like that, provided by Oracle, available in Oracle 19c. You can install it also if it's not already installed. And it's a NoSQL API. You know, the simple API where you get some documents, JSON document usually. And I will use that to show you the NoSQL approach. I'm creating a collection. This is what we do in NoSQL database. We put items in a collection, and I insert documents which are just JSON documents. If you are used to the Oracle example schema Scout Tiger, you will see that I'm putting the same data there. Basically, I created an employee collection, and I put information about employees, one JSON for each one. I commit because it is a relational database. You need to commit your transaction, and I can query it. SODA has a very powerful query syntax, which is query by example. It's even more sophisticated than SQL for simple queries. You just mention what you want, and then you can see it here. I queried employees with no existing manager, because this is something in JSON. You may have different attributes in the different documents. So here only King has no manager attributes, and I query that, of course, because he's the boss there. So that's a very simple API that you can call from Java, JavaScript, Python, everything. I'm running in SQL CL, which has also a command line to do the SODA things. I can list my collections there. I have only one just created. I can count the items. I can get with a query, like the query by example I did before, and I get the document and the key. I can also query directly with a key. This is basically a NoSQL database, a key value, where you access by a key to a document that can be small or large, usually JSON, and you put whatever attributes you want in it without any predefined structure. Okay, so I have a collection with employees, and now I want to put a bit more information in it, like in which department they work. Then I replace the documents for each employee, where I add some information. The nice thing with JSON is that you can have a nested structure. I put department there for this employee with a department number, a department name, and a location, the city where the employee is, actually the city where the department is. And I do that for all employees. This is one collection of employees with information about employees and the department they're working on. So that's good. I can query it. Like if I get employees located in a department that is located in New York, I have 3 employees there. But now you start to see the problem with this hierarchical structure. I have 3 employees working in the same department, but they duplicate the information about the name and the location of the department. So first, imagine that I want to change the name of the department or the location. It moves from New York to San Francisco, for example. Then I have to update multiple information. And the risk is that I forget one and I have something inconsistent in one item telling me that the department is in San Francisco, but in another item telling me that it is in New York. So that's the first problem. I have also a problem if I want to enter a new department before hiring any employee in it, because all the information here is with the employees. I cannot have a department that is empty. Or I need a trick like creating a dummy employee to put the department. So that's really not good. And that's where we reach the limit of a hierarchical data model like this one. It is good for one way, one view, one way to navigate from employee to department, but that's all. So now what I will do the opposite. I will create a department collection where I will put departments there For example, I create one item for the department accounting, and I put the list of employees. This is a list in JSON, a list of employees within the department. And I do that for all my departments, big list of employees in it. And good thing, I can even create my empty department with no employees. The list is empty for the moment. So that answers other use cases. But now I have to navigate from department to employees. And maybe I have some use cases which need only to work on department and other use cases to work only on employees. That's not so flexible, that's not so agile. And this is what you have in NoSQL. You need to know in advance exactly the use cases you will have. So from this structure, I can query a department by its name. I can query a department by its location, and I have the list of employees that come with it, even if I don't want them. And I can even query, for example, the department for one employee there. But this reaches the limit of the hierarchical structure, and we will see how we do in a relational database. Just before, I will introduce something that we have in NoSQL and in SQL, indexes. For the moment, I have to scan the whole collection when I search for something because I have no indexes. And I can create an index there. I will show you how to do it with this SOUG SQL-like API. I will create, so I just open the collection in Python and I call create index. My index is named my index on location, and I define where is the index. And now if I run exactly the same query and I look at the execution plan, I can see that I have an access by index. The execution plan is something that is introduced with relational databases because in NoSQL, the API is very simple. So you can really match what you do with the procedural access to the data. But we will see that SQL is quite complex, and the database will decide how to reach the data. And execution plan shows you the procedural code that the database has defined behind the query. Okay, so now I have a collection. I have to choose between a collection of departments with a list of employees or a collection of employees with information about the department. If I want something that is flexible, then that can cover many use cases, the thing I will do is split those two collections. I have one collection for departments and one collection for employees. And this basically is what we call normalization in relational databases. It gives flexibility. I will do that already in this NoSQL-like database in SODA because I can create two collections. I create first the department collection. So I've dropped the old one, which had information about the employees. And I create one where I have only information about department there. The idea is to map the collection or the table in SQL, map that to the business entity, the business objects. A department is something, an employee is something else. And then I have two collections. And sorry, I inserted department 30 and the 40, okay? And I can query departments if I want only the department. Now I will create the employees. So my old collection of employees had all attributes about departments. Now I will change that. The only thing I need there is the department number. And once I have the department number, then I can query the department collection. This is how we solve the hierarchical problem in relational databases. We split the structures, the hierarchical structure, into simple collections or tables, and we just keep a pointer and information to navigate from one to the other. I will continue put all employees there. with this simple structure. You see, I'm still in this NoSQL API, but I start to introduce SQL and relational concepts there. And even more, because this API runs on Oracle, actually Oracle stores that in tables, in relational tables. I am on SQL CL, where I can query the DDL for a table. It calls the BMS metadata behind that. And you can see that finally my department collection is a table, but not a table with multiple columns for my department attributes. It's just a generic table with an ID, some metadata about modification date and version, and all the department attributes are stored as JSON, a JSON document, in a blob, binary large object, and in a specific format, OZone, the Oracle binary storage for optimized for JSON. So finally, this is stored in a relational table, but I cannot access it directly with SQL with relational operations, because what I have in this table is just a key and a blob. You see the columns there. Same for employees. The only difference, when I created employees at the beginning, I mentioned that I wanted no as the key. And this is why I don't have the generic UID there, but the key there. Okay? So now I am in a relational database and I want to show you SQL and relational tables. Then I will create real relational tables for departments. So it starts with create table, a depth, and I will have columns there. Means that instead of just a key and the document, I will define which are the attributes of this business entity department. And I know that I need a number, I need a name, and the location. And all that can change later. I can add new columns later. You don't lose flexibility and agility when you create this structure. And rather than inserting the value, what I will do, I will insert them from my JSON collection, from my SODA collection. So I'm using the JSON table, which transforms NoSQL structure to relational structure. And I just mentioned the path in the JSON and the colon in relational. And of course, there is something more in the colon. There is a data type. In JSON, you just put strings. You don't have a date data type. You just put it as a string. Here I have number and varchars, and we will see dates, real data types, strong typing for the data types. I can query the table, and this is exactly the idea of relational tables and SQL. Storing, rather than a complex JSON with variable structure, you store everything as simple two-dimension tables. This is the most simple. This is what you have on Excel. This is what you put on a paper, just simple tables with columns and lines. And this is my depth database. One more concept in relational tables. We define the key. So we add also a key with the NoSQL. I can define the key here. Depth number is a key, but I can define multiple keys because the department name is also a key to access to one department. It is unique and it uniquely identifies a department. I can add multiple keys there in SQL, in relational tables. And I can add more constraints like this one, where I want to be sure that nobody creates a department without telling me where it is. This is the not null constraint. And this kind of constraints have multiple benefits. First one, it is declared once, and I don't have in my code to verify that the user has entered the location. I just insert, and I will have an error if it tries to enter something without anything. There is also an optimization behind that I will show you, because you tell the database that a location is always there, and then the database can optimize the access to data with that. And something else which is very, very important, when you query this table from your code, Python or Java, if you know that the column has been declared not null, you know that you will always have a value. Then you don't have to check if the result is null or not, and you have no risk to get a null pointer exception, for example, in Java. And this is very nice, because without those kind of constraints, you have a lot of codes to check if something is null or not, and you need a lot of unit tests to check that you are sure that you cover every cases. Here, just with one declaration, you know that your code can rely on the fact that each department has a location. And I will show you the optimization that is behind, again, with execution plan. So this is just a select of all departments. And if I look at the execution plan, I can see that I have a full scan on the collection. And the execution plan tells me also that this full scan has been executed once. Now, if I query department to know if there is a department without any location, the database knows that there are no departments without location because of this constraint. And then you can see that the plan still plans for a full scan of the table, but start is 0. It has never been executed because the database knows that without even reading that table, it knows that there are no rows that answers this question. Okay, I will create an employee table. Now I have my department table. I create my employee table with the columns I want. And the same, I will create it from the employee collection that I add. And I mention which JSON attributes goes to which SQL column, and with the data type. For example, when I have a date, I mention that it is a date, and then the database knows what is a date. It knows that there are some dates that are valid or not in a specific calendar. So this is my two-dimension table about employees. All information about employees. If the column is nullable, I don't have to fill it. It's like JSON, you put information on it if you want, but the thing that is important here is that I have the reference to the department there. And again, I will add some constraints there. Primary key, the employee number is a key to access to an employee. And department number not null. I do not accept any employee before it is affected to a department. And then I just declare that, and I know that in all my application, every employee has a department. And I will explicitly tell the database that this department number is a reference to the depth table column depth no. And I add on delete constraint there to simulate the same thing I had when I've put a collection of departments with a list of employees. Let me show you. I have 14 employees there. If I delete a department, sales, all employees for sales have gone. Do you want that or not? You choose. Because I defined on delete cascade, it is like a hierarchical structure where if you remove the root, you remove everything below it. Probably you want to be able to remove a department. You don't want to remove a department with employees in it. Then I went back one very interesting thing with relational databases, you can roll back your changes if you are not going to the end of the transaction. So I roll back just to run the same thing again. And I drop the constraint and I define it without the onDelete cascade. It is onDelete restrict. It's not in the syntax, but it is the default. And now if I delete the department sales, I will get an error telling me, no, that's not possible. There are employees there. So you choose, and again, this is just one declaration. You have nothing to put in your code. If you think about the number of lines of code that you need to put to verify this kind of thing, that's easy if you have a single user application. But if you have multiple users doing concurrent changes, you need to lock the structures, you need to do a lot of things. Here, the database is doing that for you. You have that in relational databases, you have that in SQL databases, you don't have that in NoSQL databases. Now, because for this normalization, for this flexibility, I've split all my information in normalized tables, one for department, one for employees. I may have to join them if I want, for example, for one employee, all the department information. And that's quite easy with SQL. I select from the table employee, which I join to department, and I just say how the join is. Means that you take employees, you take departments, and on all combination that you can do on those two tables, I want to keep only those with the same department number. Order by, because I want them ordered here by name. Again, this is a two-dimension table just for easy visualization. Why? I will show you later that we can have a hierarchical result, but it is very convenient to have full rows when you create data, because a row has the whole meaning. For example, you can read this row as employee number 7782 is called Clark. He is a manager. His manager is ID 7 something. This employee was hired in June 81. I know his salary, and he's working in Department 10, which is the accounting department located in New York. And here you see those duplicates again, but this is only in the result. In the tables, I have only one item telling me that Department 10 is accounting and is in New York. For example, if I want to change the name of the sales department, I call it Cloud Sales. And now I just run my query again. So I just updated one row in the department, and the result of my query is automatically updated and fully consistent. This department is called Cloud Sales everywhere now. So this is what is really cool with normalized table, because they are joined at runtime. You have something that is always consistent and that you can read just reading one row. Now, for the visualization, if you don't want to see full rows, like this, for example, where I ordered by department because I want the list of employees per department, if you find it not really convenient to repeat the name of the department several times, you just change that when visualizing the results, like showing department only for the first one and then the list and then showing that. I can even, by default, a join shows rows that matches both tables. But if I want to show also this department 40, which is empty, which has no employee yet, I just do a full join, a left outer join there. just changing inner join, the default to left outer join, this adds the department. And there I can really list my departments and put the employees that are there or not in the result. This is very flexible. And because it's not stored hierarchical, it's stored as different table, and the result is hierarchical, I can query the data from a different point of view. Like if I want to see the list of jobs and which employees have which job, this is still the same join. I just changed the order and the way I display it with a break, and I see the jobs and the employees there. Okay, so normalization. The idea, if you like math, you can read about normalization and the normal forms and anything, but you don't need to. You just think about the business entities, the business objects. Here in my system, I consider that department is a business entity and the location is just an attribute of it. But I may decide that I want to query more on this location, and maybe the location will be a table by itself. And maybe you will have a table with countries, with cities. The normalization will depend on what you do on your system. And basically the question is it just an attribute of a business object, or is it something that that is self-identified as a different entity? Same in employees. Probably one day you will want to have a table of jobs and just a reference to it from there. If you want to manage, for example, the jobs and the translation in different languages and anything. I mentioned that you can see the result as a two-dimension table or as a hierarchical result. You can show it as JSON, and you have function to show, for example, one JSON per row, like we had in the collection. You have function where you can show, for example, and join, and show one line, one document for each department, and then all the employees there in JSON. You can also do complex query where you want to map the relational model to JSON. It's quite easy once you have stored everything. Let me just print it. It's quite easy when you have stored things in relational tables, properly normalized, you can query it really the way you want. About joins, I will show you something that is very cool in relational databases and SQL databases. Let me just do a join there, looking for employees with department information for job president. The fact is, SQL is a declarative language. I do not tell the database where it has to start. If it has to start from departments and then look at employees, or the opposite way. In SQL, I just define the result I want, like in the query by example we have seen in SODA, and the database will decide how to get it. For example, if I look at the execution plan here, I can see that it did a nested loop join. This is just looping on employees, and then for each interesting employees, getting the department information from it. But if I run a slightly different query, job equal manager, I have more employees there. And then maybe there is a different execution plan that is more optimized for this data. And you can see that the database has decided to do a hash join instead of a nested loop, which means finally the optimizer estimates that there are a lot of employees with this job, so better read all of them, put that in a hash table, and do the join later. If you read somewhere that joins do not scale, that's probably from people who used old databases like MySQL version 5, where the number of join methods were not the same. Today, all relational databases can do nested loops or hash join and can scale join and decide depending on the data. Here is just another example for many jobs, and let's look, this is also hash join, but differently, it decided to put the depth table in hash table. We don't go into the detail of execution plan. This is just to mention that in SQL, you just declare the result you want. You don't have to code the algorithm to get it. In SQL, you say, I want the result ordered by department, and then the database will define the best way to get the result ordered. Maybe it has to store the data, or maybe it can use a structure like an index already sorted. Okay, something else that I want to show you, and that is very important in SQL. There are actually two SQL languages. One for ad hoc queries, like I did, like you will do in a data warehouse, or if you are a data scientist mining data. You type your command in a command line or if in a tool that generates SQL. And you do things like I did, like select start because I'm lazy, I don't want to list all the columns. But there is another SQL that is the SQL that you embed in a program, for example, in Python or Java. And there, you don't want to do a select star because one day someone may add a column to the table, and you don't know the number of columns, and then you cannot allocate things in your procedural language like Java or Python. So select star, this is for the user ad hoc interface of SQL. If you program SQL in your program, you just mention the columns. And I will show you something else. Here in the ad hoc queries, I mention all values directly in SQL. But if you put SQL in a program, it's exactly like when you program something that you will compile. You build your program, your code as variables in it. And then when you execute it with different values. Let me show you first what you should never do in a procedural language. So I start Python, procedural language, and I want to query information about employee number 7902, and I have this information, and then I query another one, and then I query another one. And this is really bad because everything is hard-coded there. I have 3 SQL statements which are very similar, but 3 that the database will have to optimize, find the execution plan, anything. The correct way to do that in a programmatic interface is define the program with variables, define the SQL, here just a character string with a variable. I prepare it, cursor prepare SQL, exactly the same as when you compile a program, and then I will execute it with multiple values, like this loop. I execute it, and I get the information. I get exactly the same information from it, but it is optimized to be run from a program. Okay, I'm looking at the time, no questions yet. Perfect. I will introduce a new concept that we have there in SQL, concurrency. I already mentioned that constraints on your data are very useful to verify that you enter data as you expect them. Like if you expect all departments to have allocation, you just tell the database, do not accept departments without allocation. And this is something that is very difficult to do in an application, especially when there are concurrent users and the database is shared. It has multiple users. And it's really cool that the database can manage that, because coding the consistency for multiple concurrent transactions is not easy. but testing it is not easy as well. Do you really have unit tests that test if multiple people are updating the salary of employees at the same time or something like that? That's difficult. If you rely on the database has been tested, and then you rely on the constraints. Talking about concurrency, I will do something with 2 sessions now. So here are my employees, and I will run a very simple query. Very simple if you are in SQL, not so simple if you are in a procedural language. I want to see if I have some employees who earn more than their manager. Thomas mentioned that first paper about SQL, and this was in the first paper, the example on employees department, and this query was an example of something that you can do with SQL. So I join employee amp with amp itself. Here I introduce aliases, the role of the table. I have employee table as the employee and the employee table as the manager. And I do the join, and this is why you have to mention the join there. The employee as employee has an attribute that is the manager, which is the employee number of the manager that you find in the table employee when you look at it as a collection of managers. And then I want the salary of my manager lower than the salary of the employee. And I have the list here. Scott and Ford earn more than their manager, Jones. And you see all salaries with a very simple query. We're doing the same with Python or Java, and loops and anything is probably more complex than that. But this is not what I wanted to show you. I will update data in a different session. This is just to show you this SQL in a pretty way. Okay, now I will resize the screen to run another connection as if I were another user here. And I read the table employee. Obviously, I will see the same as I had. Multiple users reading the same database. The database is shared. And this one will update the salary of Adams. Okay? And then I run the same query as I did before. Employees earning more than their manager, and now Adams is there. But if I go back to my other session there, I see the same result as before. And the reason is isolation of transaction. Okay, I increased the salary of Adams, but maybe I did not finish all the things I want to do. My intention was also to update the salary of Scott. And then if I do the both of them, Adams is not earning more than his employee. And isolation of transaction means that until I do the whole transaction, until I commit it, all the other users just see the result as before. You do not see half of the work done because that may be false. I never got the intention that Adams earns more than his manager. I just did 2 updates and commit at the end to commit the whole as an atomic transaction. Okay, we have 4 minutes left, and I think that I will just take some questions, but before I will tell you where you can see everything that I've run there and replay it. Let me just put that on the screen and I explain. Probably I wanted to quit there. Yeah. Okay. So this QR code goes to this URL where I have a Jupyter notebook. Jupyter is an environment where you can run Python, but also install other things like the Oracle client, like SQL CL, and you see the result at the same time as you run it. So this is the handout for this session, and this Jupyter notebook is on Google Colab, where you have a virtual machine that you can use, and then you can run exactly the same. And it connects to my database, but it has all credentials, and you can play on my database with that. You can also decide to create your own database in the Oracle free tier. It's free, and run the same. The only thing on Google Colab, you need a Gmail account to run that. I will show you how it looks like so that you can play with it. This is the Jupyter notebook, and you can see the queries and the results, and you can run them if you want. I'm taking one in the middle, so I'm not sure that I will get the same results. Because there are some changes before and it has to connect. Okay, so there I already did that, so I have an error, but you can run it and it connects to my database. But don't worry, you can play with it, small tables. Don't try to put too much data there. So you have all the handouts from the demo and you can play with it, do everything with it. I have put links, ask me questions on Twitter or by email if you have questions on it. I think that SOUG will put the video of this demo in on YouTube. Do you have any question? Let me check. I've lost the question pane. Q&A.
Frank, thanks for now. It was really a cool session. Very simple, the good old example that we should all know in a different form. Really nice. We've seen no further questions yet. So guys, take the next minutes to ask any of those. I suspect that many of us will be very much aware of the power of SQL. The real question is there anything you've seen where SQL becomes just overly complex, or where people go in SQL a way that is not, let's say, easy for humans to read? What's your advice on keeping SQL readable for us?
Initially, SQL was made to be easy. I've been working at CERN last year, and they still have the paper where they decided to use Oracle database version 2, so the first one. And the reason in the first paragraph, the reason is because it is simple. But then SQL has evolved, and we have many features that are very useful for data warehouses, BI, and all that. But people think that then SQL is complex. But you can do very simple queries with SQL, and it's good to keep that in mind. And the goal of SQL is not to introduce a complex language. The goal is to introduce a declarative language where you have less code in your procedural code, because a lot of things are checked by the database, and the algorithms, the loops are made by the database. So the interface is simple. Oracle is implementing more and more features on REST APIs with ORDS, and I think this is a really good solution where you provide a REST API to the developers, easy to use, this easy interface, and someone who knows better the data model will write what is behind this API, and that's, in my opinion, the good evolution. If developers, full stack developers, cannot learn all the subtleties of SQL, so it's good to divide the job.
Okay, thanks for that. If there is no other questions, we stop the recording right now. And thank you again, Franck, for a beautiful session. I cannot wait to see a SQL 201 or 301. We will see. So either you beef up the amount of data or make sure that people have a fair understanding of what happens if data is not known, or even if sets are empty, what happens. And that's, I think, really a good start to remind us that there is good reasons why SQL is so successful for 40 years now, and it looks like it will sustain for a while. Thanks for the session, and we have a little break now until Ralph is ready to start. See you.
Thank you very much. Bye.
Thank you, Franck. Bye.